All right, so we're back in this part of an analytical balance discussion, and I just left you off with the idea that sooner or later we're going to have to make sure that these balances are working the proper way. And these are either going to be the internal route, which is what I will do and the balance will do, or it will be more of an external route that we call preventive maintenance, or PM. So, how would I go about making sure that the balance is working the proper way after we've purchased it, used it in our lab, time has went on, months or maybe years? How can I make sure that that balance is still doing what the balance should be doing? So, what we do as users is that we use a series of calibration weights. So, this is what a set of calibration weights look like, right up here in the top right hand corner. So, very often they will come with a assortment of different sized calibration weights that each weigh different masses. And what we would do on our end as a user is every now and then, and maybe daily, we would take one or more than one of these calibration weights and we will put them on the balance. So, for instance, what if this little bitty one right here to the left weighs 1 gram? I would take that 1 gram calibration weight, I would put it onto the balance, and I would wait for a few seconds, and I would look at my display. Hopefully there's no drift on the analytical balance, and that number should be very close, if not exactly 1.0000 grams. That's the purpose of a calibration weight set. Now, as you can imagine, there's different types of these calibration weights, but these things are very important, and all labs, including academic labs, should have a calibration weight. This helps ensure that the number that we see on the screen is actually a truthful number, and that the balance has not just crazily one day decided to give made-up numbers left and right just like a student would, right? Okay, so what you're seeing on the screen here is the same thing. They come in different sizes: 1 gram, 2 gram, 5 gram, 10 gram, 100 gram, 50 gram. They go all the way down to 1 milligram sometimes, which is just like a little bitty fleck of metal that you would put onto an analytical balance. Most of the time, these checks with the calibration weights are done at least every couple of weeks. And then sometimes in heavy regulated laboratories, these calibration weight sets could be used daily. So what that would mean is that in the very early morning, before anyone uses the balance at all, someone would take a calibration weight set and they would pick out one of the calibration weights that the procedure tells them to do, and they will put it onto the balance just to double check that it's reading the same today as it was yesterday. These calibration sets, folks, they're not very cheap. Typically these things, $1,000, if not more, way more, depending on the type of calibration weight set that you get. But it is something that is very often required for a laboratory to work the proper way. Now, the $1,000 ones, those are not the cheapest. They do come less expensive, and you can find them on Amazon. I mean, if I want to use that as an example, for way less than $1,000 a piece. But the problem is that they are not certified. So what this means is that a proper certified calibration set would be, okay, this is 50 grams, and this has had extremely intensive tests by third-party organizations that is 50 grams, just the way it's stated on the calibration weight. That is what a certification means. Well, non-certified means that, yeah, you've got 50 grams. They've made sure that it's 50 grams or at least close to 50 grams as much as possible, but they did not go through the trouble of getting a third-party group involved to certify those calibration sets. And that is not proper for industry. You will never find non-certified calibration weight sets that are out there. However, for us, that is typically okay. We don't need to go that extreme and extravagant. Again, it's all about saving the taxpayer money. So we have calibration weights. They are not certified calibration weights, but they do a pretty good job for us to kind of showcase this process of calibrating and ensuring that a balance works the proper way. All right, so we did have 10 of these sets at one point in time. The problem, though, is that they get stolen, they go missing, pieces and parts begin to start disappearing from the calibration weight sets. Sometimes this would happen overnight. And then, we scratch our head and we wonder, well, how do these things disappear? Well, maybe students are taking them. These calibration weights would be great for little top loader balances that you put in your pocket that you want to kind of measure out some ounces of an illicit drug and sell it on the street. And then, of course, maintenance also has keys to our laboratories that come in and out. So I'm not blaming anybody. It's just awfully strange that a lot of these things disappear during the time that we are not in the laboratory. But that's why somebody would steal them. That's why someone would have a need for them, to make sure that they're not gypping somebody or getting gypped themselves when they measure out an ounce. All right, so up next is just a close-up picture of what these calibration weights look like. This is a pretty standard shape. The reason that this kind of divots here on the very top is that you never, ever, 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 ever want to use your fingers to pick these up. All right, never use your fingers because your fingers are filthy and nasty. I don't know where they've been. You probably don't know where they've been. They come with grease and nasty lotions and everything else. Who knows what you've touched throughout the day? And all of that will transfer mass onto a calibration weight. And we cannot have mass transferred onto a calibration weight because then we think that the balance is off, and it's not. It's just you're a filthy animal and you have contaminated something that we need to be using in a laboratory that has to stay clean. So the reason that those divots are up at the top is very often we take a pair of tweezers and we use tweezers to pick these calibration weights up, sit them down onto the balance, record the masses, then take the same pair of tweezers and then grab that calibration weight back off of the balance pan and lay it or carefully sit it back into the case that it comes in. All right, so that's the proper way to handle them. You never touch them with your fingers. We prefer you not to touch them with the gloves either, and the reason is because sometimes those gloves have loose powders on the outside of them to prevent them from sticking to each other. So that's also a transfer of mass, and that is why we often prefer something like tweezers that are staying clean and dedicated for this purpose to handle these calibration weights. Only at the top. Nothing more. All right. So there's different calibration weight sets. They come in different categories and classes. And what you're seeing up here in the very top table, I want you to focus on this very last row. And this very last row are the classes of calibration weight sets. So they go from class 1, 2, 3, 4, 5, and 6, all the way up to 6 actually. But you're seeing up here in the very top, it looks like they go to 5. But look, here's class number 6 down here at the very bottom. All right. So there's a couple of things that I want to say here. The lower the number, class 1, that's almost like an A in the class, right? So class 1 is going to be the best. So very often if I'm working in industry, I'm looking for class 1 calibration sets because that class is the best of the best. Your first place. So class 1 is first place calibration set. The higher up that you go, that second place and third place and fourth place and fifth place and sixth place, those calibration sets get worse and worse and worse. So if you look at this very top line, this says reference standards. And these are reference standards that are industry grade reference standards that have been double checked by third parties to ensure that if it says 10 gram, it really is 10 gram. Very often, those are classes 1, 2, 3, and possibly 4, but you need to read the descriptions of the calibration sets because they will tell you if they have been certified by another company. So that has to be part of the description. For us, we do not want to splurge money and get these calibration sets. We do have some of these in our lab, but we don't let students use them for their purpose of training. But we have student set of calibration weights, and the student use is very often class 4 or 5, one or the other. So most of the time when you see a listing that says class 4 or class 5 calibration weight, it will say nothing about being regulated or standardized or certified by a third party. Nothing like that is going to be part of the description because they assume that you know what you're buying, and most people don't. But think of this as first place, second place, fifth place. Class 1 is the best. They're the most expensive. They are the certified ones. And then class 5 are often the worst. They're not certified, and they could be dirt cheap. Now, down here at the bottom, you're going to see something that we call tolerance. So the tolerance for the standardized calibration weight sets basically means error. Okay, how off would they be? So for instance, I can do a calibration set and class 1 is supposed to be the best. So that means when I put that weight or that calibration weight onto the balance, I should get that mass. Yes, I should be getting that mass. That's how that's made. It is certified. But I know there's wiggle room. I know there's slight room for error. There's error with everything, folks, right? There's error with using the balance. There's error with the balance. There's error with the transfers. There's error all around us in a laboratory environment. So what the tolerance does is it tells us a little bit about the error that I might expect as far as the mass goes. So for instance, let's say that I take a 50-gram calibration standard. So here's the 50-gram calibration standard, and there's class 1 and class 2 and class 3, class 4, class 5, and class 6. So what you're seeing with the tolerance, aka error, is that as we go up in the class, the calibration set gets worse and worse and worse and worse and worse. And the tolerance is a plus or minus. So that means it could be over or it could be under. So my window gets bigger. So that means if I have a class 1 50-gram weight, this should be plus or minus 0.12 milligrams of what 50 grams is supposed to be. I can go under 0.12 milligram or I can go over 0.12 milligram. But somewhere in that very, very tight window is class 1. That tells you how good they're supposed to be. I mean, they're supposed to be spot on, folks. That's why you pay so much money for those class 1 calibration weights. Now, if I go to class 6, which would be more of a student type of use, then class 6 gives me a plus or minus tolerance, an error. And what that means is that that error is plus or minus 7 milligrams, not 0.12 milligram, 7 milligrams. This calibration weight could weigh 7 milligrams less, or it could weigh 7 milligrams more than what is stated on the calibration weight. Now, for student use, for academic use, that might be perfectly okay. I mean, we don't probably need to go better than that, but for industry grade calibration weights, this is not going to call the shots for us. We do desperately need that class 1 whenever we can get a hold of them. So what happens here is that the window, which is my plus and minus as far as the gram goes bigger, right? And it has to go bigger because this is not as well made as a class 1, and this is kind of willy-nilly. We think it's kind of 50, but we're not kind of sure if it's 50, but we think that it's kind of close to 50. So why don't you just give us your money and we'll send it to you? That's what class 5 and class 6 is all about. So keep in mind, those are numbers in milligram. So here, over here to the side, what you see is that it's the 50 milligram standard. And if you look at class 6, that is 7 milligrams. So that's plus 0.007 or minus 0.007. So here would be the range that would be accepted for that particular standard weight. And actually, this is a mistake. So if I take 50 plus 0.007, I'm going to get 50.007, right? I mean, that kind of makes sense. That's easy to do in my head. But if I take 50 minus 0.007, that is not 49.003. So I want you to double check that number in the calculator, because this number, Tracy made a mistake. Oh no! But I do that very often. So just take 50 minus 0.007 and you'll get the proper mass range that calibration weight should fall in. All right. So that's kind of a summary of different classes of calibration weights. It's also a little bit of insight about what this tolerance is supposed to be. And the higher number that you go, the worse you get, the worse place that you get, and the more room for error that you're going to have. What I'm going to show you next is something that we call a standard operating procedure. And this is something that you might see as you're working for a laboratory company out there. Notice up here at the top, it says Clean Gene Standard Operating Procedure. Standard Operating Procedure is abbreviated as SOP. So this is an SOP that someone would follow. And SOPs come along with everything, right? Even how to use a balance, how to clean something, how to clean off a lab countertop bench. I mean, there's an SOP for that. There's an SOP for everything. So here, if I take a look, it says, with tongs, place the standard on the weighing pan. I now know why it says tongs, never fingers, never gloves. Wait until the stability detector disappears. So this is written in terms for the actual balances that we have in our actual lab. They are written to be specific for the laboratory and the company that you're going to be doing these procedures in. Next, read the results. Then it says record the daily verification on form QF 15.3.6.3 with your date, time, and your name. So this is basically the company's way of saying, yeah, we're going to do this every day. So we're going to have a calibration weight that is going to be dedicated, and we're going to take that weight, we're going to put it onto the balance every morning, and we're just going to double check to make sure that balance is providing a proper number like it should be day after day after day after day. Because like with everything, as you use it, these things can mess up if you're not careful. All right, so next one says the balance is now in the weighing mode and you're ready for operation. So for the operation, this is just an SOP to talk to us about how we can go through and measure out something on a balance pan. So it says remove the load from the weighing pan, make sure it's zeroed or tared, then place your sample on the pan, then wait for the stability detector to disappear, then read the result, and then if you're finished, press off. Turn the balance off, so that way it doesn't waste energy and it doesn't use kind of the electronics component of the balance. Walk off, leave it, have it ready for someone else when they need it as well. So that is what we call an SOP. SOPs come along with everything. Again, even something as simple as how to measure something the proper way on a balance. As far as the internal adjustments, I've mentioned this before in a previous video, but for the most part, modern analytical balances have what we call an internal adjustment that takes place as you start the balance up. Or if you go into the menu of the balance, you can initiate this and the internal adjustment will take place after it has been on. So we call these internal calibrations. This doesn't really require a calibration weight set. There's actually something already built into the system, built into the balance. It does this on its own, and it's almost like a backup or a double check because they know that some people have no clue that you're supposed to calibrate your balances all the time. I mean, I've been in laboratories for years, and they've had no clue that this is what you were supposed to do. They've had those balances for 15 years and still think they're working fine, and they probably aren't, or they're not really calibrated like they're supposed to. So a calibration kind of menu option will show up on these balances. Very easy to perform. As a user, I go into that menu, I choose internal calibration or calibration, and then there's a self-check mechanism in the balance. It knows that something is supposed to mass a certain way, and then it just double checks itself, and then it will finally adjust the mechanism that gives you that display readout until that number matches what that kind of standard calibration weight is supposed to be. So you initiate it on the touch screen of the balance. After that, internal weights are going to be used to cross-reference those values, and then it will self-check itself. It will probably display OK or give you a confirmation that the internal calibration check is now finished. But all in all, folks, this does not take place or substitute for the external ones that we are supposed to do as a user, because those things can mess up as well. You know, if someone picks up an analytical balance and they drop it, or they knock it over, or they damage it in some way, then these internal adjustments, they're not going to do you any good. So we always have to third-party check everything, and in this case, we are going to be the third party. So internal calibrations are great. Those are things that you can do just as a quick measure to make sure that you're in line. But I'm still, as a user, required to take these external calibration sets and put those calibration weights onto the balance pans and record those numbers to make sure they are in line with what needs to be there. All right. Now, as far as taking care of the balance, you know, what kind of part of my job as a laboratory worker, what should I be doing to make sure that the balance stays operating and making sure that we are minimizing the downtime and all of the maintenance that has to take place here? So number one, clean, 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 clean. I mean, I can't say that enough with everything in the lab. So as far as the analytical balance goes, you want to make sure that the inside of the balance pan stays completely clean. Wipe it down, sweep off the powders. You want to make sure that everything in that chamber doesn't have any residue or any kind of sticky liquid that can eat away some of the metal or that can stay behind, because that's going to be the number one problem, just messiness of you weighing out things. So after you work with the balance, you want to make sure that you check for all of those residual chemicals that might be left behind. If you do, sweep those out of there with like a little makeup brush, wipe them out with chem wipes or paper towels. If they're larger spills, you need to tell someone about it, because then the balance has to be completely taken apart. We've got to do a complete deep clean from top to bottom with those. So 5.4.1.2 for this particular SOP. For this company, it says each week the unit should be wiped down with general purpose cleaning agents, and sometimes that can just be simple as water or some type of alcohol. Then it says wipe down the pan, wipe down the base plate, and wipe down the sides and the lid of the balance. And I'll show you where those things are in just a second. Next, it says if you do have a chemical spill, that's okay. Mistakes happen, right? Some accidents are going to happen as you're using these balances, especially in the beginning. But if you think that it's bad enough and you're working with pretty dangerous stuff, then you need to call hazard control. Now, this is for this particular company. The company will have their own mechanism in place for you to respond to these accidents as needed. But this company wants you to call a control team to come out and kind of clean that mess up for you. They know, they're trained in that kind of thing, and most of the time you're not. So leave it to the professionals. Next, this company is requiring a semi-annual calibration. So this would be a more full-blown external calibration used on the analytical balance to make sure that it's continuing to work the proper way. Next, the initial and the semi-annual calibration should be performed by trained service department personnel. All right, that is just a confirmation to say, leave it to the professionals, right? I mean, if you want to go redo a bathroom, that's great. But when you go in and start redoing your plumbing, do you really want to be the person in charge of that? Do you know what you're going to be doing? Or would you rather leave it to a professional to come in and do it for you the right way the first time through? Okay, same thing here with analytical instrumentation. Next up, it says if the balance is out of calibration. So out of calibration calibration. OOC is the abbreviation that a lot of companies will use for that. It says that the balance goes out of commission. No one can use it. There should be a sticker on it that prevents the use of it and says, nope, no go, not today until we actually fix this, calibrate it, and get it back into commission. So out of calibration is a big deal. So that means that us as users need to treat the equipment like it's our own, and we need to take care of it on a daily basis, because if it goes out of calibration because of things that I have done with it, it completely stalls everyone else that needs to use that balance until it needs to get fixed. So it slows down the entire company if you are not careful. Finally, it says form SOP needs to be filled out every time that a repair happens or every time a calibration happens. We have to keep track of this. So not only do these forms require the date, of course, but it also requires the time. It also requires the person's name that did it. And very often it requires a justification, like what was going on with the balance? Why did this get initiated? What did you see happening that you did not like? We need to write those comments down, and then we need to double check that the balance is actually providing us a proper number after the fact. All right, so we're almost done, but I've got a few images that I want to show you first. Here is a picture of an analytical balance that has been taken apart. So the base here really comes into a box. I just take the styrofoam out. This goes onto the lab counter. It sits down perfectly flat. And very often there's always a level bubble that's there up on top that I can take a look at to make sure that these things are in fact level. If not, these do have adjustable feet that I can kind of screw to make them higher or lower in order to get that balance pan level, because level is going to be key. So make sure that when you use a balance, you always double check that bubble. Make sure it's always in the middle of where it needs to be. If not, we need to level it, because there's a chance that those balances get moved throughout the day or throughout the week. On top, this is our draft shield, is what we call that. So this draft shield is all of this glass encasement that prevents those drifts from happening, those drafts from happening, protects the sample from you, and protects you from the sample in a way. So those just kind of sit on top. If you look here, they just lower down onto the middle of this base, and then you normally twist them. And when you twist them, that somewhat locks them into place, so that way they just don't freely just lift off without a little bit of effort at least on your part. A lot of them will have a locking ring here on the inside. So once you lower this down onto the base and give that nice twist, then very often you'll open these doors up and you'll put your hands in here, and there's a plastic ring most of the time that you twist as well. And that is a locking mechanism that even prevents that base from coming up and off even more so. So with that said, once it gets locked into place, once it's secure, then the next thing that goes on top of that will be this thing that we call a drip ring. So this drip ring does just that. It protects that inner mechanism. If you have some solid spills, if you have some liquid spills, the purpose of the drip ring is to prevent that solid and liquid from getting down into the electronics of the base. Next, after the drip ring goes in, then we have the weigh pan that sits on top of that. That has to freely move up and down, because if it doesn't move up and down, folks, you're not really going to get any type of mass that comes off from your balance. On the backs of these balances, no matter what they are, they're typically made a very certain way. They're all somewhat universal in a way. So here we see a cord for the power plug that goes into the outlet. I mean, it's electronics, it's got to have power. And then here we see an Ethernet hookup as well. Think of this as like your internet at home, right? You got a router. That router is connected to some type of Ethernet cord maybe, or your computer runs by an Ethernet cord. This is a networking cord. So if you do have something like LIMS, that Ethernet cord is going to be very handy for you, because that's how you get it connected to the server that the company is running off of most of the time. All right. Over here to the left-hand side, you see a USB connection and a RS-232 connection. Those are typically for the same reason. It just depends on your setup and the way that you prefer to run your cables. These instances both, well, they can go directly to a computer. So the RS-232 can be connected to a desktop computer. The USB can directly be connected to a computer and or a balance printer. That is how these things get hooked up. So once more, the balance printer can be connected by USB, or the balance printer can be connected by RS-232. So that's the purpose of those. Nothing special, but I do think it's important sometimes to talk about connections and how all of this kind of connects into a bigger main working laboratory. On the screens of the analytical balances, you'll often see this kind of view, maybe not identical, but at least something similar. Here we see a printer icon that is going to send a trigger to an external printer, so a balance printer. So that way, whatever number shows up here on the screen, that's the number that's going to be printed off on the receipt ticket. Here I see something like an icon of a calibration weight, and if it's not that icon, they might just list CAL for calibration. That is where we would go to do the external or the internal calibrations. We have the balance to go into those respective modes. So once I press the cal button, it will say, what do you want to do, internal or external most of the time. And then I can have my choice of which one I would like for the balance to perform. If I want to do an external one, then I need to make sure that those calibration weights are ready to go. Next up is the menu up here in the top left-hand corner. That menu icon will let me go into the balance and set things like usernames, passwords, dates and times. And yes, there are chances where I will have my own username and password to log in order to use the balance. And that's how these companies know who's measuring out what, when did it happen, what time did it happen, and we can put a lab analyst name onto it because you've logged into the balance to tell them that kind of information. Here to the right-hand side, you will often see some type of like selection or arrows that go up and down and left and right. This is to maneuver mainly in the menu icon when you go into those options. And then finally, an enter key. So that's very often in the menu option to accept a certain answer that the balance is asking you. That is an enter key, just like it's an enter key on your keyboard at home on your computer. Finally, the biggest, most important button is down here at the very bottom, and that is the tare button. So the tare button is the 0 button. So whenever I go to the balance, I always make sure that it is tared, that it is reading 0.0000 for me, and I press that button and I'll wait. And what I should see on the screen is, sure enough, 0.0000, or however many number of decimal points that balance goes to. All right, so here in the next kind of last few minutes, we probably are going to give you a laboratory assignment that will focus on an analytical balance. And it's going to lead you through some of these proper processes of putting something onto a balance pan, weighing it multiple times, using different types of balances, and even using calibration weight sets. So you'll get that procedure probably within the very first week of the CTC 114 course. And if you look here, here's the real world example of what we're kind of thinking and the purpose of what we're doing in a lab. So it says in lab environments, weights from an analytical balance are common wet laboratory procedures. It's important that an analyst understands how to properly use one. Additionally, the use of calibration weights is important in routine lab work. So let's pretend like you're employed by a local pharmaceutical company. They're preparing you to become a metrologist, which is someone who can calibrate and maintain instrumentation. Great jobs, by the way, for some of our graduates because we're so instrumentation based. It says your first assignment includes getting yourself familiar with the balance. Your supervisor has told you to follow a procedure just to understand the basics and how to report accuracy and precision. So this is where I'm going to kind of leave off the video with this example problem, because we've just said something, and that's accuracy and precision. So here we have a class problem, right? This is something similar to what you'll do in the lab. And it says, suppose that you are verifying the performance of a balance. We want to make sure that it is in line doing what it needs to do. The technician weighs a 10-gram standard, a calibration weight, 6 different times. And here are the numbers that they're going to get. 10.0002, 002, 001, 002, 999, 998. A, what's the average mass? B, what's the standard deviation? And C, the balance says that your precision should be equal to or less than 0.001. Does it meet that specification? All right, so a couple of things I want to say here before we start kind of this math problem. Oh God, math. Oh no, I hate math. All right, so first is this 10.0002. I'm going to look at this as an outside user, and I'm going to go, no, this doesn't make any sense, right? Because all of these other masses that you have reported has 3 decimal places, not 4. This particular one has 3. All the way across, 002, 001, 002, 999, 998, and then I get this one weird bogus number that's got 4 digits. So I would go to that lab analyst and I would say, no, listen, you recorded this data wrong. This is probably a bogus number. It doesn't make any sense. It doesn't fall in line with what the balance is actually supposed to read out. It's only going to give you 3 decimals based on these other values. Why did this one give you 4? So because of that, I'm going to look at this, and after clarification, that lab analyst is going to say, well, yeah, I actually made a mistake. It should have been 002, not 0002. So we're going to make the assumption that they had the receipt ticket from the balance. That proves that it was 002. But the reason I do this is to make you actively think about what the data is trying to tell you. Now, when we do the math, I don't want you to do a calculator. We're going to do Excel because Excel will do it for us. So here, I have opened up Excel. There's nothing in it. It's just a blank Excel spreadsheet. And I want to go over some of the basics of using Excel for you. So I'm going to drag this screen maybe down. And here are the values that we're going to be keying into Excel. And I just need to kind of do that in any way. It doesn't matter what order. I don't really care. Just somewhere in Excel. It doesn't have to be up here in the very first box of A1, right? It can be anywhere it wants to be. So I'm just going to kind of shift it over a little bit just to prove that point. And I'm just going to use the keypad on my keyboard, and I'm going to type in those values that should be there. So 10.002, and then the next one is another 10.002. All right, so 002. And then my next one, my third one, is 10.001. So I'll key that one in. And the only thing that I'm doing is kind of clicking in the box down below after that, or hitting enter, and that will take me to the box down below. And then we have 9.998, enter. And then my next one is 9.999, enter. And then my next one is 10.002, enter. All right, so those are the values. And question A says, what's the average mass, right? So once I took this calibration weight of 10 grams, I weighed it 6 different times on the same balance. It wants to know average. All the numbers added up divided by how many we have. I mean, that's what the definition of average is supposed to be, right? So all of these numbers added up, and then we have 6 measurements, so we would divide by 6. Well, Excel actually has this integrated within the spreadsheet system already. So the only thing that I have to do when I want Excel to do a calculation, I start off with equal. So I hit equal, and then I'm going to type the word average, A-V-E-R, and notice it's showing up already there. I'm just going to go ahead and finish it though, A-V-E-R-A-G-E, average. So I'm going to open up a parentheses on the keyboard. I mean, that's number 9 on your keyboard, right? Open the parentheses up. And then with the mouse, what I'm going to do is I'm going to go to the first data point, and I'm going to click it. And I'm going to hold the mouse down, left click, hold it down. And then I'm going to drag the mouse down to highlight all of the data that I have typed into Excel. And then I'm going to close that parentheses up, right? That's the number 0 on the keyboard, just shift 0. Close the parentheses up and hit enter. So it has done a calculation for me already. It's already added them all up. It's already divided by 6. It's as simple as that. That's the power of a spreadsheet. We're not in math class. We don't need a calculator. We'll use Excel for all of this. Notice that all of these decimal points here are 3 digits. So therefore, I should make that value 3 digits as well. I need it to kind of look all the same. So up here in the very top, I'm just going to drag this out a little bit further for you. Up here in the very top, you're going to see an option that allows you to shrink the number and to increase the number. So if you look at these arrows that go left and right, you'll see 0.0 and then 0.00. Watch what happens when I start pressing those arrows up at the top. So it's highlighted. That's the Excel that we're going to mess with. And then as I hit the left button, then that number gets bigger and bigger and bigger and bigger, right? As far as decimal goes. And then I want this to kind of be matching the rest. So I'll just want 3 digits after the decimal. So I'm going to shrink this down until I get 3 digits after the decimal. So what it does is that it properly rounds for me. And then that's the value that's showing up based on the Excel calculation that it's done. All right. So that is the answer to part A. What's the average mass? Part B says, what's the standard deviation? All right, so this is just as easy. So I want Excel to do the calculation. So I hit equal. Then I type the code STDEV. That stands for standard deviation. Notice all the options that show up. Don't do any of those options. Just STDEV. Open the parentheses, just like we did before with average. And then I'm going to go up here and left click and then drag down, highlight the data that you want a standard deviation with. Close the parentheses and hit enter. And there's the standard deviation. Just like before, I want the number here to match the number of decimal places. So I'm going to shrink this number down. So I'm going to click that cell, make sure it's on the number. And then I want that value to be shortened until we get to 3 decimals. And there we go. So my standard deviation, and I'm just going to write that beside of that, right? I can type in words. It's fine with Excel. Not a big deal. There's standard deviation, and then here is average. So what does standard deviation actually mean? Standard deviation means how close your values are to each other, all right? So if you're throwing darts at a dartboard, and all of your darts are hitting in the same location every single time, you have very good standard deviation. There's very little differences in the way that you throw those darts. The same thing happens in a laboratory. If we're doing measurements and it's the same measurement every single time, my standard deviation needs to be very low. So low numbers are very good here. That's what we want to see. So that is what we call standard deviation. That's its purpose. And that also goes by another term, and that other term is called precision. And that's something that we've talked about before already in previous lecture videos. All right. So the question here is for B, what's the standard deviation? We just answered that. And then finally for C, it says, well, the balance says that the precision, aka standard deviation, needs to be equal to or less than 0.001. Does it meet it? And if I look at my standard deviation here in this example problem, no, it doesn't. So that means my balance is not providing me a consistent number every single time that I weigh the same thing over and over. It's out of calibration. It's out of specification. So that means I need to do a little bit of work to figure out what's causing this to happen in a laboratory environment, if that is the criteria of that balance as it was made and manufactured and sold to me. So until we figure out how to fix that problem, that balance would be out of commission until we actually repaired it, got it back working like it should be from day one, and then we can take the sticker back off and start using it in a laboratory again. All right. Okay, so that is my kind of intro to an analytical balance lecture. Maybe it's some things, I hope at least, if you've had classes before, that these are certain things that are new, that was new information that you've never heard of before, and if so, that's great. That's the purpose of the lecture. So in the meantime, what will happen is that we will meet face to face, do some of these lab experiments using a balance, and then we'll kind of break away from the routine maintenance, the routine kind of things for a balance, and we'll do some fun things with an analytical balance too. So I'll see you in the laboratory. We'll do some analytical balances labs together, see how this process works and calibration standards work, and then we're off again for another lecture video a little bit later on.